Hi friends, in our last session we have seen Introduction to Compressor. In today's session we will study Reciprocating Compressor. This is Faizan Kagvi and I welcome you all to our lecture series of Basic Mechanical Engineering. So let's begin with our topic of Reciprocating Compressor. So what is Reciprocating Compressor? So we would say that a compressor in which piston reciprocates inside a cylinder. Okay, now this compressor has two strokes in order to achieve high pressure air. First stroke is called a suction stroke, second stroke is called delivery stroke. So as you can see on your screen, I have shown a diagram of reciprocating compressor in which a cylinder, piston arrangement, then connecting rod, crank and crankshaft is shown. On a top side, inside a cylinder head, there is a spring-loaded inlet and exhaust valve, which are operated by means of a spring. From one side, air inlet is shown, that is air is going to enter, and from other side, air outlet, which means compressed air will get out from this cylinder. Now let's see what happens in a suction stroke. During this stroke, piston will move from top dead center to bottom dead center. Okay, at that moment of time, inside a cylinder, vacuum will be created. Because of a vacuum creation, a pressure difference will be established and spring operated inlet valve will open and atmospheric air will enter into a cylinder till piston reaches its BDC position. So the entry of air takes place because of pressure difference. This is called a suction. Okay. At that time, crank will perform half rotation. Okay. In the next stroke, that is called a delivery stroke, piston will move from bottom dead center to top dead center. At that time, whatever air that has been sucked will be compressed because piston is going to move in upward direction, inlet valve will get closed, whatever air is present, its pressure will increase, its temperature will increase, and finally we can achieve compressed air on a top side of a cylinder. At that moment of time, spring loaded or spring operated outlet valve or exhaust valve will open and highly compressed air will get out from a cylinder and will enter into a receiver, that is called air receiver. So these two are the most important strokes. This shows that how a reciprocating compressor is going to operate. Now further, reciprocating compressors can be operated by two ways. In a first case, we are going to study two cases basically. So in a first case, we are going to consider compression without clearance volume. We know that we have studied during IC engine that a clearance volume is a region between a top dead center and a cylinder head. Right. So that volume is not present, so that is our first case. So let's see that case. So for this without clearance case, I have shown a pressure versus volume diagram. Okay, now whenever compression is done, we are going to consider certain process because air is considered as a ideal gas, right? So we can apply gas laws in this case while designing a work input to a compressor. We know that compressor is a power absorbing device, so definitely work input is done and after that only we can achieve highly compressed air. Now in this case, just visualize that there is no clearance volume, which means top dead center and cylinder head are at the same line. Now this I have represented on a PV diagram. You can see pressure versus volume diagram. TDC I have shown at a zero volume, indicating that let's say this zero volume represents a cylinder head, and since there is no clearance volume, so we can represent that even by our top dead center. And on another side I have shown a bottom dead center, which is going to be a volume which will be covered by a piston during its stroke. Okay, so considering our first stroke, in this without clearance case, suction stroke moving from TDC to BDC, so that I have represented on a PV diagram from a point 4 to point 1, representing the suction stroke or motion from TDC to BDC. A point 1 is achieved. Okay, remember that we would say we have completed one stroke. Now in a second stroke, compression is going to be achieved, that is our delivery stroke will be performed. So considering that a compression is going to take place adiabatically. Okay, so adiabatic compression is represented by a hyperbolic curve, right? So I have shown a line from point 1 to point 2 representing a adiabatic compression. Now at point 2, we would say that piston has not arrived at its TDC position, and at some intermediate position of a piston we have achieved our required delivery pressure, that is our pressure P2. Let's say our required pressure which we have achieved is 10 bar. So at point 2 represents the pressure which we have already achieved. Now this is based on a hypothetical condition. We are assuming that further motion of a piston towards the TDC will open our outlet valve, and at a constant pressure air will be delivered and will get out through the cylinder. So this is actually represented from our point 2 to point 3 shown by this horizontal line, representing that at a constant pressure air is going to be delivered to a air receiver, finally reaching a point 3 which is a representation of a TDC. Our stroke has been completed, suction stroke and delivery stroke. Okay, this is one cycle which we have completed. Now in our first case we have to determine that how much is the work input done. So we can say that whatever is the area covered by this graph on a PV diagram, this line represents the work input to a compressor. So let's find out. So we can say that for adiabatic work done per cycle, that is capital W is equal to area 1, 2, 3, 4. Right, that is an area which is covered representing work input. Now splitting this area in a following terms, as I have shown that area under 2 to 3. So see line 2 to 3 carefully. That line, and we can visualize that entire area. Okay, so that area plus area under 1 to 2. So see line 1 to 2, that is a compression process. So area under that curve. Okay, so how much area is covered? So entire 3 to 2 area. Okay, and second 1 to 2 area has been covered. But now we would say that even you can see area under 4 to 1 which is not in our work input condition. Right, that is not an area which we have to consider. So what we are going to do? So that additional area which has been added up has to be subtracted, which means area under the line 4 to 1 has to be cancelled out. So for that I have subtracted area under 4 to 1 from our total area which we have considered for this curve. Now just think that how we can determine the work done for area under 2 to 3. So we can say that 2 to 3 is going to form a rectangle, right? So I can say that length into breadth, right? So how much is the length? So we would say the length is V2, seeing along a volume axis, right? And how much is the height? So we can say the height is P2. So the area for work done will be P2 V2, right? For area under 2 to 3. Similarly, for area under 1 to 2, so 1 to 2 is our compression process, and we know that work input for adiabatic compression from our properties of gas chapter, it is equal to P1 V1 minus P2 V2 upon gamma minus 1, right? So from that we can use that equation to determine work input. Similarly, now what is area under 4 to 1? So now see carefully the area under 4 to 1, again it is representing a rectangle. So what is the formula to determine area of a rectangle? So it is again length into breadth, or we can say length into height. So how much is the length? So if you see carefully, the length is V1, and the height is how much? So the height is P1. So we can say the area for this rectangle 4-1 is P1 V1, which means the work input, or we can say the work which has to be subtracted is how much? P1 into V1. So let's see further. So you can see I have written P2 V2 plus P2 V2 minus P1 V1 upon
gamma minus 1 minus subtracting the area under 4 to 1, that is P1 V1. Now you can clearly see we can arrange these terms in form of P1 V1 minus P2 V2, right? So further in the next step, what I have done, I have arranged the term that is in form of P2 V2 minus P1 V1. So finally the equation is going to become gamma upon gamma minus 1 in a bracket P2 V2 minus P1 V1. Okay. Now in a further next step, I have taken P1 V1 common out. Okay. So in the next step, gamma upon gamma minus 1 P1 V1 in a bracket, it is going to become P2 V2 upon P1 V1 minus 1. Let's say this is our equation number 1. Okay. Now seeing further steps, so as we know that P1 V1 raised to gamma for our process from state 1 to state 2, P1 V1 raised to gamma equals to P2 V2 raised to gamma, which is a law of adiabatic process. So from this equation, we can say that V2 by V1 is equal to, actually it is equal to P1 by P2 raised to 1 by gamma, but I have taken reciprocal, so I can write it is equal to P2 by P1 raised to minus 1 by gamma. Now why I have to do this? So equation number 2 has to be substituted in our equation number 1. So after substituting, we get work input to a compressor equals to gamma upon gamma minus 1 P1 V1 in a bracket P2 by P1 raised to gamma minus 1 upon gamma minus 1. So this is our formula to determine work input to a compressor for our case of adiabatic process. Now let's see our next type of process, that is our polytropic process. Even we have studied that is a multiple process which can be covered. Okay, so for a polytropic process, as we know, the polytropic index is small n. So the equation is going to remain same, the technique is also going to remain same. Just we have to replace our gamma of adiabatic process by our n of our polytropic process. So the equation is directly written as work input to a compressor for a polytropic process equals to n upon n minus 1 into P1 V1 in a bracket P2 by P1 raised to n minus 1 upon n minus 1. Okay. Now similarly we can determine a work input to a compressor for our isothermal process. That is, if a compression is done according to isothermal process. So now in this case we need to determine that. We know the formula of work done, that is area under the curve 2 to 3 plus area under curve 1 to 2, if you remember that, minus area under the curve 4 and 1. So over here I have written the same equations. P2 V2 is the area under 2 to 3 process. Okay. Then compression is according to isothermal. So we need to use a formula of work input during isothermal process. So what is that? So it is P1 V1 ln V2 by V1. Remember we have determined that equation, right, for state of a process from state 1 to state 2. So over here I have written P1 V1 ln V1 by V2. Actually we can write final volume upon initial volume, but if we write final volume upon initial volume, so the value of log will become negative, and when a negative value is added up, so the answer will be reduced. So we just need a numeric value. For that I have written V1 by V2. Okay, minus P1 V1. Now since in our isothermal process we know our law of isothermal process, that is P1 V1 is equal to P2 V2. So from this equation we can write that work done is equal to, we can say that P2 V2 and P1 V1 both will get cancelled out, and the final equation will become P1 V1 ln V2 by V1 by V2. Okay, and further we can write P1 V1 log R, where R is, we would say, compression ratio. Even further this equation can be written in form of characteristic gas equation. So we can write PV is equal to MRT. So further we can even write MRT ln R.
Okay guys, so I hope that you are clear with the concept of reciprocating compressor and our this case, that is compression without clearance. So today we are keeping up till here. In our next session we will continue our second case of compression for our reciprocating compressor, that is compression with clearance volume. Okay, so till then stay tuned and thank you all.